Very good afternoon to everyone present here. I am Sahil Dholakia and I'm one of the general coordinators for Mimamsa 2025. I would like to extend a very warm welcome and express our gratitude to our judges for this round, Professor Srinivas Hota and Dr. Anirban Hazra. They have been present throughout the framing and the verification of the questions, and I would like to thank them once again on the behalf of the question making team. We have our four teams. We have IISc, IIT Bombay, IIT Delhi, and IISER Kolkata. And for the audience, for the participants and the judges, I'll very briefly go through the rules of this round. So the total time for this deep thought is going to be 2 hours and 30 minutes. There'll be a total of 4 questions, and the order of the teams will be decided through the draw of a chit. The judges will choose a chit, and the first team will be selected. Now, the team will get to choose a question. Now, after they choose a question, it will be displayed and read by our podium coordinators. You will get 15 minutes of time to think. During this time, you're not allowed to present on the boards. After the 15 minutes are over, the first team or the directed team will get 5 minutes to present their solution on the board. Subsequently, the next team will get 3 minutes, followed by 2 minutes and 2 minutes. Apart from this, the maximum number of marks which a team can get for the directed question for this round will be 20 marks, followed by 10, followed by 5, and 5 for this round specifically. Apart from that, in this round, I would also, again, I think the teams are already aware about this round, about the rule that please not repeat solutions from the previous team. Add something new, because only that will be considered for evaluation. I think we are set. If you do not have any clarifications, I'll hand it over to Kush and Henrik, who are the podium coordinators for the chemistry deep thought. The floor is open to you guys. Thank you. All the best.
Good afternoon. I welcome everyone to Chemistry Deep Thought of Mimamsa 2025. My name is Henrik.
And my name is Kush. We will be handling the podium for this round.
We'll first like to introduce our judges. We have Dr. Anirban Hazra and Dr. Srinivas Hota. Professor Anirban Hazra works on theoretical and computational chemistry, specifically the chemistry of molecules in excited states. He is fascinated by physical chemistry because it allows him to see the everyday world in an extraordinary way. He is also passionate about science education.
Dr. Srinivas Hota works on organic chemistry, particularly glycosidation. He is a fellow of the Royal Society of Chemistry and has won several awards, including the Young Scientist Award of the CSIR and INSA, and the National Teachers Award. We thank both of them for being here today.
We request our judges to pick a chit to determine the team that gets to answer a question first, and we will proceed clockwise from that team.
IISER Kolkata, you'll be going first, followed by IISc, IIT Bombay, and IIT Delhi. We are all set for chemistry deep thought. Presented on the screen are the 4 questions for this round.
Life of pi, Cataplexy cycle, 3-body problem, and Khullja symptom. Okay. IISER Kolkata will be going forward with the question Khullja symptom. Vatsal, working with proteins, has designed a biomolecule which is hollow from inside and is flexible so that it can open under force, as shown in the schematic below. This molecule ends in thiol groups at both ends. Vatsal used spherical magnetic particles, 2 of which can perfectly fit inside this biomolecule. When a suspension of MPs is subjected to a magnetic field, the particle accumulate due to the attraction between them, creating bigger lumps. However, once the magnetic field is switched off, they remain as lumps. He went on to read this system as shown in the following simpler schematic. All the reactions are taking place in a phosphate buffer. However, this self-assembled structure formed only when light of 365 nanometer was illuminated. This biomolecule is not affected by the light. To understand this better, he performed a scattering experiment with B where scattering intensity is directly proportional to the number of particles of a particular size. Consider that only MP is responsible for scattering in B. Question 1. Predict the formation of B and thus explain the nature of the graphs shown. What do you think would happen if in place of the malamide derivative we use the following compound? Out of curiosity, Vatsal introduced sodium
Sodium ethylene diamine tetraacetic acid, NADTA, in the solution medium, and when he measured the scattering intensity, he surprisingly obtained a graph similar to that in the case of 3 MPs. To study this further, he synthesized a red emitting dye, P, as follows. P fits perfectly inside the biomolecule. The circled substituent gets hydrolyzed in presence of an enzyme named esterase. Consider there is no reaction with the anionic I- part. When the biomolecule containing P was introduced to both NADTA and esterase, we do not observe any red emission. However, the red emission is preserved in the absence of NADTA. Question number 3. Propose a possible mechanism for the formation of P and thus explain why the addition of NADTA caused the quenching of the red emission. IISER Kolkata, do you have any clarifications about the questions? Yeah, you have 15 minutes to solve the question. Your time starts now.
Team, you have 5 minutes remaining. Teams, you have 1 minute. Teams, your time is up. Team IISER Kolkata, kindly come up on stage and present your answer. You have 5 minutes. Your time starts now.
So for the first question, predict the formation of B. So what we have done is that the thiols groups are there. So it will react on the electrophiles that are the carbonyl carbons. So the amine will be released, and this group will become an integral part of the biomolecule. Now, when we are exciting with the H nu, this is the homolumo gap that will get excited, because of which now this will form a chelate with Mg2 plus, which is given in excess, and we get this B. So this is the mechanism that we propose. Explain the nature of the graphs shown. So as we can see over here, for the first case, first let me start with free magnetic particles. So as it is given in the question that before magnetization, it is before magnetization, nothing is happening, of course. After the magnetization has been done, then the size comes over here because they form a cluster with the free magnetic particles. And even when the magnetic field is off, the same thing remains. Now for B, that is this molecule, the thiols are no longer open. So it is not an open system where the magnetic field can pass through. Now it is a closed system because of the magnesium 2 plus on top, which is forming a chelate. Which is why now the size may increase a little bit because magnetic field can pass through, but very little, and hence we almost find no difference in the graphs. For question number 2, this is the answer of question number 1. For question number 2, if we use this thing, the only difference between the dye given in question number 1 and the one that is given in question number 2 is the presence of this double bond. As we have said in question number 1 that only on excitation by the 365 nanometers light does this get excited from the pi to pi star, which means that in the absence of this pi bond, this won't get excited, and as a result, no reaction will take place ultimately. Because this is not going, there is no conjugation, obviously. For the third reaction, we have to propose a possible mechanism for the formation of P.
One minute left.
So this is the mechanism for the dye P that we propose. So this thiol will do an addition reaction over here. The water will go out, and obviously the second part will happen in the presence of a base, obviously. So that is why we have added base and DMF. Now explain why the addition of NaADTA caused the quenching of the red emission. That is simply because in the
30 seconds
presence
left.
of the EDTA will form a chelate over here. There is acetate. So acetate can actually lock this ester bond, because of which now the red emission will be quenched, as this is the LUMO that we are talking about. So pi to pi star emission, pi star to pi emission will no longer take place. So that is the answer for our question. Thank you.
IISER Kolkata, your time is up. IISc Bangalore, kindly come up on stage and present your answer. You have 3 minutes. Your time starts now.
So our idea for the solution is that in the first part, the basically the thiol group would be attacking this double bond here, and so we have the protein here and the thiol groups are here. So basically this complex, it will get bound to these thiol groups, and after this we have the reaction will be like this. So we have O minus here, which will extract this proton from here, and again there is Mg plus 2. Due to that Mg plus 2, two neighboring thiol groups can get attached to each other. So basically, due to this, we will have the thiol groups will get locked with each other due to this complex, and this complex will become a part of this biomolecule. And because we have this locking, the MPs which are inside this biomolecule cannot go out. So that explains the part that explains the graphs for the B. Before magnetization, magnetic field is on and magnetic field is off. And because in the second question we don't have this double bond, and by our proposed mechanism, this thiol group is attacking this double bond. As there is no double bond, we will have no reaction.
One minute left.
For the last question, the esterase is unable to bind to P. The esterase is a protein designed for the initial molecule present over here. So
30
red
seconds
quenching. Red quenching is not observed in case of just the esterase. However, EDTA forms a complex with P, which is why red quenching happens. Pita.
Team, your time is up. IIT Bombay, kindly come on stage and present your answer. You have 2 minutes. Your time starts now.
We propose that the SH over there binds to the double bond and forms a acetal-like structure with sulfur instead of oxygen. This then binds to two of the SH molecules on the enzyme, due to which it creates an inward force preventing the MPs to go outside and form lumps. And this explains why in case of free MPs we can find a shift towards the right in the magnetic field, whereas in the B structure we're not able to, because they're not able to escape outside. And then for the second question, because there is no double bond present in the given structure, it won't be able to react with the SH, and thus the MPs will be able to move outside and form lumps, and we get a similar graph. And the reason why SH is attacking over here is because this is anti-aromatic, and then upon acting of SH, we get the anti-aromaticity is lost and it stabilizes the molecule. In the second case, there is no double bond, so there is no reaction and there is no anti-aromaticity in the molecule as well.
IIT Bombay, your time is up. IIT Delhi can come up on stage and present your answer. You have 2 minutes. Your time starts now.
Yeah. So in the presence of NAEDTA, I would like to borrow their structure. So the double bond O will just form like the EDTA will get. So this will just be a single bond ketyl type structure. Same for this, due to which it will not form a complex with Mg2 plus, and also uh, instead of that the Mg2 plus will form the double bond will form a complex with Mg2 plus only, leading to non-complete coverage of this, due to which the it will exhibit a behavior similar to the free MPs. And for the second one, mm, wait, LH connected, NH connected. Yeah, so I think the addition of NADTA caused the quenching of the red emission because it locked the C double bond O, which was wait, addition due to which the color was observed, and because it lost the double bond character.
IIT Delhi, your time is up. The floor is now open to the questions from the judges.
No, so I just, if IISER Kolkata could repeat, what was their explanation for that, for the scattering graph? What did you say?
So the explanation for the B or the free MPs?
For both, I mean, for
This
the,
one.
yeah.
For free MPs, it is basically that since the biomolecule is in the tube form, so when the magnetic particles are free, that is when the reaction hasn't happened. So because of the magnetization, obviously clumping will happen, the size will increase, and after the magnetization is also switched off, it just remains like that. But when it is for that B, so B is basically this compound. So overall, this sulfur will be, reacted to all of this, and the magnesium will come on top of all of them. So it will be more like a closed structure, or we can say a less open structure will be formed, which will limit the number of magnetic lines passing through it, which is why the magnetic particles getting magnetized will also be limited, and the same pattern we can observe downstairs as
Okay.
well.
Okay.
Thank you.
If I have to, can I give them the point structure, or I shall not tell them? Okay. The thing is, overall, IISER Calcutta, your approach of showing the one is really wrong, because if you look at the most electrophilic center in the N-maleimide is the double bond and not the carboxylic acid that you have taken. Okay, so that is the point number one. And then the second thing is that is supported rightly by IISc Bangalore, and you guys were right in identifying that reaction is called as Michael addition reaction or 1,4 addition reaction. It's not going to attack on the carbonyl group, so you will get partial marks and then you won't get anything for that one. But of course, you said that no reaction happens for the two, which is not, your explanation is wrong, because if you are attacking on the double bond, if you are attacking on the carbonyl, then it should happen irrespective of the presence of the double bond. Okay, so your explanation of no reaction is correct, but your explanation of why no reaction is wrong. No, it's not going to happen like that because as they have proposed, the Michael addition won't happen there at all. Okay, so, and the third one, your explanation about two graphs is not really appropriate. You said that when demagnetization happens, we expect the particles to come back to the normal earlier state, but it is not happening. Why was it not happening? That's the question. And you just said that it will not happen. That's it. Okay, and for those graphs, none of you have given any kind of explanation. And IIT Bombay also has identified Michael addition in their explanation, but previously IISc Bangalore has already given the clue, so you won't get any points for that one. And you guys did not. It won't form the way you have written, but actually your trigger is the Michael addition only. You are doing double Michael addition kind of thing, which will not happen. Because once you attack that double bond with the Michael acceptor, then what happens? You no longer have a double bond there. So the double bond move forward and then it goes to the carbonyl. So there is no double bond. So your explanation of giving that dithioacetal kind of thing is not really correct. Okay. And but of course they have already given the explanation about no reaction with reference to the compound that does not have the single bond. So their explanation is correct. So you won't get anything. And IIT Delhi, actually, you also got trapped between carbonyl reactivity versus the alpha beta unsaturated double bond. So you won't get any credit for that one. Yeah, that's it. And regarding nobody has found that one. What is that esterase? What esterase does is that it cleaves off the esters. Okay, it's basically a biological saponification reaction. So it just cleaves off that thioacetate group, and then that becomes a ketone. And then when you add magnesium to that, what happens is that it is going to chelate, and then when they added that pyridine, 2-amino 3-hydroxypyridine, so it will start cyclizing and then does something there. So none of you have given that one. Okay. Yeah. Once they don't know that structure, after that EDTA thing will. Yeah. So now I call upon. Oh, we are not. Okay. Okay, I think we can go to the next one.
IISc Bangalore, it's your turn now. Please pick the question. Oh, it's team. Three body problem. Akash loves to work with challenging species. He started a synthesis with a pentachloro substituted cyclopropane ring and a strong base, followed by the addition of excess amine, producing an aromatic product B+. The net effective yield of product B plus Cl minus was very low when he did not use the secondary amine in excess. Following reaction scheme is given. Question number 1. Propose a possible mechanism to help Akash understand the formation of products A and B plus Cl minus. Generally, benzoic acid is insoluble in dichloromethane. Shockingly, when he added some B plus Cl minus to the mixture, the acid dissolved. Here, dissolution is due to the formation of an enhanced number of non-covalent interactions. To understand this, he used a pi molecular orbital diagram where he combined the 2pz orbital of the ring carbons as a set of 3 group orbitals, A plus E in G1, and the pz orbitals of the 3 exocyclic atoms, which are immediately bonded with the ring carbons as another set of 3 group orbitals, A plus E in G2. These orbitals and their interactions are represented in the following MO diagram of B plus. Question number 2. Using the MO diagram as a reference, explain his observations. Note that the A2 HOMO has a high energy. One of his colleagues, Kush, saw the potential in this newly synthesized compound and suggested emission of these molecules. They tested 3 choices of the following compound and recorded their respective molar absorptivity coefficient at their absorbance maxima, epsilon, along with a property with value V. For a molecule, V depends directly on the epsilon, but inversely on the number of internal degrees of freedom, along which the motion is not constrained. They knew that the LUMOs of phenyl, benzyl, and naphthyl groups have slightly higher energy than A2, the HOMO for B+. Question number 3. Help Akash and Kush understand the trend in V. Finally, Akash wanted to perform a CN coupling reaction with B plus as the catalyst. The following reaction scheme was followed. Observe that 2 is a radical dication, whereas 3 is its excited state. Question number 4. With careful analysis of this catalytic cycle, propose a possible mechanism for the reaction and thus predict the unknown product B. With careful analysis of this catalytic cycle, propose a possible mechanism for the reaction and thus predict the unknown product P. IC Bangalore, do you have any clarifications about the questions? You have 15 minutes. Your time starts now. 5 minutes left. One minute left. Teams, your time is up. IISER Bangalore, please come up to the stage and present your question, solution. So you have 5 minutes. Your time starts now.
The first reaction from the given cyclical ring to A is a dehydrohalogenation reaction, base catalyzed, followed by substitution of the chlorine at the position opposite to the double bond by the amine, which a two-step elimination of both the chlorines, which forms a aromatic compound. While he's drawing the diagram, for question 2, the HOMO in this case is the HOMO participates in hydrogen bonding with the benzoic acid, thereby forming intermolecular hydrogen bonding, disrupting the dimer, which makes it more soluble in the solvent, because the net product is more polar than the benzoic acid dimer.
In the third question, if we see here, the nitrogen here is sp3 hybridized. Here the nitrogen the lone pair of the nitrogen will be deconjugated along with the benzene ring. Here also the lone pair of the nitrogen will be deconjugated along with the benzene ring. So basically we are reducing the number of degrees of reducing the number of internal degrees of freedom. But here we see that here there is an ethyl group. So in this while there is only a phenyl group here, now there is a benzyl group, here is an ethyl group. So here the rotation is less constant than this, because this naphthyl group cannot come along this, then there will be repulsion between these two benzene rings. So here the motion is most constant, here moderate, and here it is least constant. Now according to the question, the V depends inversely on the number of internal degrees of freedom along which the motion is not constant, and while it is directly dependent on epsilon. So the internal degrees of freedom decrease, so the V increases, and also epsilon also increases, so V increases.
So to clarify the first part, firstly, elimination reaction happens and we can see this double bond gets created. Then the lone pair of nitrogen on the amine attacks on this Cl and substitute. After that, as secondary amine is present in excess, that will act as a base and will consume HCl from this compound and forming this product which has only two electrons inside the ring, so it will be an aromatic compound. And when it is not, when the not present in excess, it will not be available as a base to consume the compound. Compound will not be formed in excess.
Also, the aromatic compound is stabilized by resonance. Also, for the fourth question, we aren't able to solve it completely. Magar, from what we know, since the HOMO is basically the lone pair on nitrogen in this case, following the free radical, following following electron emission, it will form a free radical on the nitrogen atom, which reacts with benzene to form a benzene free radical. And aage ka mechanism? Nothing.
30 seconds left. IISc Bangalore, time is over. IT Bombay, please present a solution. You have 3 minutes. Your timer starts now.
Okay, so first what happens, concentrated KOH is an eliminating a reagent, so it will eliminate a Cl and form a double bond. So initially we have this structure. It will eliminate a Cl and an H to form a double bond here. And then OH minus will act as a nucleophile and add on these two Cls, and two OH minus, two OH are unstable, so then it will form a double bond O like this. And this is our product A and the mechanism for it. And then for forming B,
Yeah, so we get A like this, then when it here we get a structure like and then this bond goes here. So finally we get B, which is aromatic. Yeah, and for the third part, we can see in this degree of freedom is basically constant to just this bond which has free rotation. These two bonds don't have free rotation, so there is very less degree of freedom here. Here we have multiple bonds with free rotation, plus these bonds in these rings can also alternate, adding to more
You
degrees
have
of
1 minute
freedom.
left.
For the third part, it's similar, but here there is an extra benzene group. So when it uses its free rotation, it would cause steric hindrance with this group, and hence it would have slightly less degree of freedom than the second part. So first has the least degree of freedom, and second has the most. And when we also take into consideration the values of epsilon which are given, the value of V follow us this order. And like, yeah, in the first one we have a very low epsilon, but V is like almost comparable to the second, which shows that it has a much lesser degree of freedom than second, which is good. And for the second and third, taking into account the values of epsilon, we have that second has slightly lesser degree of freedom than third, which I also.
Your time is over, IT Bombay. IT Delhi, please present a solution. You have 2 minutes. Your time starts now.
so we basically are in agreement with the IISER team. Like for the first question, the first step is dehydrohallucination, which will result in this, and subsequently a bisubstitution will happen here, which will create a geminal diol, which will effectively make this, and this when so this is basically A, which when reacted with NHR1R2 in excess will create this, and Cl minus, this being a B plus. And for the third part,
So the absorption maxima for the first one is due to the carbon, and here for this phenyl ring and for this biphenyl, because the number of conjugations are more, you can clearly see the trend of the absorption spectra. And from the first to second, when we go, there is a high increase in the degree of freedom because of this bond rotation, and also in this and this. And since epsilon also epsilon is also highly increased, the change in V is almost negligible. From the second to third, as we go, as previously mentioned that because of steric hindrance, there is not much, there is not much, there is, due to steric hindrance, the degree of freedom decreases, and so V has increased much more.
IT Delhi, your time is over. As a Kolkata, please present your solution. You have 2 minutes. Your time starts now.
For the second part, as we can see, the molecular orbital diagram, we have the A over here, the E over here, and another A over here, which is the HOMO. And the answer for the first question, B plus is basically this. So what we are getting is that this A being the HOMO is doing an electron transfer to the benzoic acid, forming a hydrogen bonding. This is a D3H structure, which is why we are getting that the benzoic acid dissolves. Now for the third question, what we are having is that the first substituent is a typical chair-like conformation. The typical chair-like conformation is much more foldable, which is why their internal degrees of freedom is less. And the second and third question also just like the same internal degree of freedom. For the fourth question in particular, so what is happening is that an electron is getting out from the A, that is the HOMO. Then what is happening, a photon is coming out and this A is getting excited to E. So there is one electron in E after all, which is reacting with the benzene, and benzene is getting radicalized. And after that, we are getting a 4+2 cycloaddition
Your 20
with
seconds
the
left.
with the substrate over here. So
IISER Kolkata, your time is over. The floor is now open to questions from the judges. Seeing as we have no questions, we request a member of the question making team to come up on the stage and present the solution.
Hello, hello, hello. Is it on? Hello. Yeah, so nice try everyone. The thing is that for the first part, it does do dehydrohallucination. So can I rub one of the push? Yeah. So the first part, it does do dehydrohallucination. Now, one thing you have to understand that in a cyclopropane ring, these bonds are extremely strong. So they cannot just be replaced by an amine group. That is why I have given excess amine rather than 3 p valence. So what it actually does is it firstly forms a hydrogen bond, which lowers the sigma star of this orbital. Then this nitrogen load pair can attack the pi star, pi to sigma star, this will go ahead. The same thing happens over here. So at the end, the product that we'll actually get is this one. But all the nitrogens are present over here. I'm not drawing the other parts for the sake of time. For the MOT, the thing is that since A2 is a high-lying HOMO, this is in comparison with the chloride 3pz orbital. That is why they would actually have an orbital repulsion. Because if you have two HOMOs very close in energy to each other, they really cannot combine with with each other. Like they will prefer to have ionic or rather orbital repulsion, electronic repulsion rather than just directly combining. If you just draw the A2 of this high-lying HOMO, firstly, it will be like out of phase in this part. These parts will be in out of phase. Then the chloride lone pair, like this is the 3pz, this will form an orbital repulsion. Due to this Cl minus is naked enough to do hydrogen bonding with both benzoic acid and DCM. That is how they dissolve. And you have CH and you have a chloride over here. This dissolves. That is, so these compounds are basically known as ionic liquids, which are liquid at room temperatures, and they have conductivities almost in comparison to, suppose, sodium chloride in water. For the second part, yes, some of you have given interesting answers. This does not have that much of a rotational degrees of freedom. All of them have vibrational degrees of freedom, so we don't need to discuss about that. Epsilon value for this one is much less than the epsilon value for this one, and this one just skyrockets to 64,000. The thing is that I mentioned that V is proportional to epsilon. So in the second substituent, the V value decreased since it has a lot of rotational degrees of freedom. In this case, actually pi stacking happens. So if this is the molecule, and then you have the same naphthyl group over here. These do more pi stacking than two benzene rings. That is why this has more restricted rotation, and that is why you have lesser number of degrees of freedom, so V value increases. The second part actually, the last part. Even if you did not find B, you could have solved this one in a way that the first one that is happening is B2 plus, so it's a dication radical. It gets in an excited state, it gets converted to just one cation. So the only way to balance this equation, if benzene has one cation and one radical, which will look like this. And then this pyrazole derivative, the lone pair will come here, and this will attack over here. See, this H plus has gone away. That is given that H plus is going away from here. Now one electron goes away because there is a radical. It will become plus, and it will just gain back its aromaticity. So this was the final product for the last question. Yeah, that is nice try. Thank you. Huh? Oh yeah, yes sir.
IIT Bombay, choose your question. Life of pi. Sumangalam synthesized a dye with some modifications following the reaction scheme given below. He calculated that the absorbance maximum for C was greater than that of B, whereas E had a much lesser absorbance maximum. Interestingly, both B and D emitted red color, exhibiting almost identical absorbance profiles. Question 1. Draw the possible mechanism for the formation of A. Predict the structures for C, D, and E, thus explaining Sumangalam's observations. Wanting to explore the chemistry of this new dye, he went on to perform a series of reactions as follows. In all the cases, DCM was used as the solvent. Here, catalytic amount is abbreviated to CAT-AMT. Help Sumangalam predict the products P1, P2, and P3. All the products are structural isomers. Why do you think that the yield of P3 is almost negligible in presence of C? Question 4. In presence of E, catalytic amount, and blue LED, P3 formed is lesser yield as compared to that when B was used. Why do you think so this happened? Do you have any clarifications to me? You have 15 minutes. Your time starts now. 5 minutes left. Two minutes left. Thirty seconds. Teams, your time is up. IIT Bombay, kindly come up on stage and present your answer. You have 5 minutes. Your time starts now.
Okay, so our mechanism for the first part is that first the N double bond O, which is over here, it will be present as a plus here and minus here, which will delocate. I'll make it red. So we have N double bond O here. So this will be present as N plus O minus, and this will be in a resonating structure. So this plus will delocate here, and this other pi bond will also come here, and plus will come here then. And as N is present here, it will donate the lone pair to it, and this will be formed. So after this is formed, this O minus better base, so this H will transfer there, and what NOH. Now this has become a good living group, like in diazotization. Similar structure was being formed, and it forms a living group. And in the other part, the second structure, okay, in this what will happen, we'll get a minus here, plus here, and this plus will come here, and because AR2 is a plus M group, because it has a OMe, so this plus will be stable here, and this negative will attack on this nitrogen, and this OH will leave. So what we will get finally, the product is and yeah, so this will be the final product that we'll get as A. Now after it is reacting with BF3 ET2O, and it forms B, and according to us the possible C is, yeah, this, or it can this bond can also be broken, and it can exist as
minutes
this
left.
also, because this reaction may be similar to the HBO reaction, where we add BF3 and Hg plus 2, and E can be, the BF3 hole is removed and is replaced by H, so instead of there will be a H, so I'll draw it again. And yeah, so this is how A is formed, and C and E. For D also, the product would be similar to C according to us, because Hg plus 2 and Zn plus 2 react similarly, I think. Hg.
Thirty seconds.
The, uh, next part, we have this structure. Here we can form a carbon ion. It would be an aromatic intermediate. Then it can act as a
IIT Bombay, your
nucleophile.
time is up. IIT Delhi, you can come up on stage and present your answer. You have 3 minutes. Your time starts now.
So for the first one, first there would be intermolecular rearrangement. Yes, to positive of the addition of
In the fourth one, in the fourth one, the product E will be similar to product A. It will be exactly the same, and it's a very bad Lewis acid which will not interact with the double bond O, which is present in the reaction, due to which this will not participate properly, and P3 will not be formed that much.
For the next part, the first reaction with DCM at 80 degrees will just be a simple dialder, which will give us this product. In the next part, what happens is the oxygen of the C double bond O donates a lone pair to AlCl3, making that site electron deficient. So the diene will donate electrons to perform a reaction with that as a dienophile. So once we do that, we get this a product similar to this. And in P3, what happens is the Lewis acid B is not as strong as AlCl3, so not any of these occur, but both C double bond C and C double bond O are almost equally electron deficient. So we get a product which is formed by this cycloaddition.
So in third, the yield of P3 is almost negligible due to, we can use HSAB principle for while differentiating between Hg2 plus and Zn2 plus, due to which, we can use HSAB for the BF3 and the Hg2 plus compound, and we can see that the interaction of BF3 will be more with oxygen and less with the Hg2 plus, where these are the structures.
IIT Delhi, your time is up. IISER Kolkata, you can come up and present your answer. You have 2 minutes.
So
Your time starts now.
So the mechanism for the first question will go like, we have acetic acid, so this will be protonated. So now it becomes nucleophilic. So the
30 seconds left.
Transition is happening to 14, and since obviously either we have the much lesser
IISER Kolkata, your time is up. The floor is now open to the questions from the judges. Oh, sorry. You have 2 minutes. Your time starts now.
So we are trying to find P1 and P2. So for P1, we have this compound in DCM and at 80 degrees Celsius. So now here there are two hydrogen atoms, and one hydrogen will be abstracted, proton will be abstracted to give this aromatic product. So see, the formation of this is highly favored because this is aromatic, and now we have this compound. Now we have to check where this minus, where this would attack, in which double bond this would attack. This double bond is very much favored because this the carbonyl the CO double bond is very much polar, and so there is a large delta minus charge. There is a large delta minus over here and a large delta minus over here. So this minus can attack on this carbon. It can attack on this carbon-carbon pi bond also, but that is not favored because if the minus attacks here, then there will be a minus. There will be a minus here, and between carbon-carbon pi and carbon-oxygen, nucleophilic addition is always, this is basically nucleophilic addition. Nucleophilic addition is always preferred on CO because of its larger polarity. So it will attack like this.
Thirty seconds.
And it will abstract proton. So it will finally become this.
The P2 is just a standard Diels-Alder reaction.
IISc Bangalore, your time is up. The floor is now open to the questions from the judges. We request a member from the question making team to present the correct answer.
Hello. Hello.
Yeah, while he is preparing, can I ask a question to IISER Kolkata? You said that mercury will be coordinating, copper 2 plus will be, Cu 2 plus will be coordinating, and Hg 2 plus will be coordinating. Can you write the coordination site of that? You said that it will be coordinating with the nitrogen, but there are several nitrogens there, right? One second.
Yeah, sure.
There are several nitrogens. Which nitrogen?
Hello.
Okay, thank you. Yeah, go ahead. Now you can go ahead.
Let me just rub. Please don't mind, I'm rubbing your phone. So again, nice try. For the first part, a mechanism of this sort is happening. So you need to understand that the pi star of this N double bond O is open to attack. So the lone pair will go here, here, and something of this sort will happen. Now the thing is that there is HOAC in the medium. So it can easily take this H and produce OAC minus from here. So this is OH, this is H, and then we have double bond. Here one, two. This OAC minus will abstract this and just, give away OH minus from here, because in the medium there is already MUH. The same thing. Now when Hg2, actually compound B is referred to as the ASA body pi tie, and in these type of dyes the nitrogen boron bond is extremely strong. So you cannot just take away it and you cannot just introduce Ag2 plus in the medium and the B plus B minus will be replaced. What exactly happens is you have so there is a specific reason why I gave this pyridine moiety. Here is that benzene and OM, benzene OM. Hg2 plus can perfectly fit over here and perform non-covalent interactions with them. As a result, this structure now becomes much more rigid and more delocalization can happen. Previously, this dye was emitting in the red region around, and now it will emit in the NIR region. For Zn2 plus, this Zn2 plus is really small as compared to Hg2 plus, so it wouldn't completely fit over there. So there is a very weak chelation between a Zn2 plus and the 3 nitrogen pincer type setup. For H plus, only this one will get protonated. So in overall, we have reduced conjugation, and therefore the emission peak and the absorbance peak will have a hypsochromic shift or blue shift. The second question is just direct Diels-Alder. Diels-Alder is a concerted mechanism. So it will of course want to react to this CC double bond. So the product that you will get is something like this. We have OMe over here. So it is exo with, so it is in this conformation such that there is lesser number of steric strain present within the within this ring itself. When you add AlCl3, this O can effectively bind with LCl3, forming a Lewis acid base adduct. Now this CO bond has become labile enough. The pi star LUMO is low enough such that this sigma bond is in perfect alignment with this. So this lone pair will attack the sigma star of this, sigma will attack the pi star, then it will open up. So ring expansion. Again, this sigma is in perfect alignment with the same pi star of this CO. Sigma star, O will attack, O will donate, no, O, sorry. The OAL sigma bond will donate to the CH sigma star, sigma to pi star, then ring pi. Then this comes apart. So this is what P2 is actually. This is P2. Due to presence of AlCl3, this is the major product now. Whereas when AlCl3 was not present, P1 was the major product. In absence of AlCl3. Now the body pi dye is actually a photosensitizer. So it can actually allow the the allowed reaction of 2+2 cycloaddition, which happens in presence of light. So this will be the product for the P3. Homolytic friction cannot occur over here because this is a polar bond. So this will just do a 2+2 cycloaddition with this one and this one. Then you have double bond. Whereas now the thing is that in presence of B, this had enough energy to do. When you apply C in catalytic amount, the absorbance peak and the emission peak has already shifted in the has done red shifting. So there is not enough energy to allow this reaction to occur. That is, they do not get this product at all. Maybe a very negligible amount. And since there is 80 degrees Celsius, you get P1 back because that is a thermally allowed Diels-Alder product. In presence of E, the emission peak has blue shifted, so it has more energy to go to the reaction. Therefore, side products can form, for example, it can form a 4+4 cycloaddition with this one. Or it may even form 2+2 cycloaddition with this one. Due to formation of these side products, you do not get the 2+2 cycloadduct that I just talked about. So that is it. Thank you. Yeah.
IT Delhi, it's your turn now. You'll be moving with the question Cataplexy cycle. Jagdish wanted to create palladium-based catalytic centers. To start, he performed the following reaction scheme. Question number 1. Predict the structures of A, B, and C. Here, THF is used as the solvent. Now, he took iron-containing spherical particles. The crystal structure of the edge of these particles includes Fe3+, sites with one coordination site unfilled. The following schematic summarizes what he did. The contestants are informed to correct this mistake in the questions. Each spherical particle has numerous C bonded to it, but there will be a 1:1 bonding between a molecule of C and the spherical particle. Question number 2. Identify how this self-assembled structure will be formed by portraying a well-defined diagram. You can show just a part of the structure, but it must be well-defined. Now, he created several PD2+ catalytic centers with Na2PDCl4, immobilized by the organic shell. To exploit the potential of such a system, he performed the following syntheses. Stoichiometrically, P1 required 1:1 stoichiometry of the substituted p-nitrobenzene to 1,2 diphenylacetylene, while P2 required half, 1:2. Changing the solvent surprisingly changed the product. For R is equal to H, a complete catalytic cycle for P2 and a partially complete catalytic cycle for P1 have been shown. Jagdish noticed that the DMF molecule can replace one of the chloride groups and is forming a labile enough bond with PD center. Question number 3. Keeping this in mind and taking a reference to the given catalytic cycle, draw the possible catalytic cycle for the formation of P1 and thus predict the product. Hint, P1 contains a fused ring. Question number 4. Suppose R is kept as NH2 with reference to the catalytic cycle for P2. Can you predict the product in this case? There is formation of only one exclusive product for this. What could be the possible reason? Further, what do you think would happen if NO2 was used as R? Team IT Delhi, do you have any clarifications regarding the question? So you have 15 minutes, the time starts now. 5 minutes are left. We have 2 minutes left. Your time is over. IIT Delhi, please come to the stage and present the solution. You have 5 minutes. Your time starts now.
Yeah, so A will be formed by additional elimination on the ring. Um, yeah, so one molecule of this will attack here, and since there's a nitrogen here, it can accept this, and once this happens, an elimination will happen in which Cl leaves. So this will repeat 3 times, and we will get um, this. Now when yeah, so for part 2 what happens is we have Fe3 plus, and when there is excess OH minus added, we get there is a particle which has Fe3 plus on the surface. So when the ultrasonication happens, we get OH minus adsorbed on this particle, and C might contain some groups which can bond with the which can form hydrogen bonds with the OH minus. So we might get a structure in which there is C which has hydrogen bonds at the surface.
Yeah. So this will be the structure of P1. So what is the process that is involved in this? So the process will be similar, like the third process will happen. Then there will be cyclization, like
2 minutes left.
yeah. So the cyclization will occur like this. This bond will go wait, draw next.
30 seconds left.
All right, this is P1.
I can tell your time is over. IISER Kolkata, you have 3 minutes to present a solution. Your time starts now. One minute left.
So what is happening over here is that so aniline attacks on the palladium, removes the chlorine. So what we get is
30 seconds left. IISER Kolkata, your time is over. IISc Bangalore, please come up on the stage and present your solution. You have 2 minutes. Your time starts now.
We agree with what IISER Kolkata drew for compound A, but we slightly differ in compound B. According to us, the compound B should be and now the A is this.
One minute left.
Similar structures will be here, like this, and this Cl, so this part is basically, we can regard this as RCl plus NO. So this should get replaced and C would have a structure like this.
30 seconds left.
similar structures here.
IISc Bangalore, your time is over. IIT Bombay, please come on the stage, present your solution. You have 2 minutes. Your timer starts now.
So for the fourth question, for the fifth step, we can have basically two possible pathways. One is it can directly form this like how it was forming in the initial one, or it can form to this one. Following
1 minute left.
in the sixth step, this can directly lead to the similar product which is given over there. Just that in the benzene ring below, there will be a amino group as well. In this case, if these two bonds get cleaved, it will form a very large ring, and because of the instability of large rings, it will form this bond instead of this to this, and this will also give us a similar product like this. And in case of NO2, because of the strong minus R effect, there will not be the third step which is taking place, and hence we won't get a product.
Basically, in the first question, for the formation of A and B, SNAR mechanism will be used, and similar, like as the other team, IISER Kolkata said, similar product will be found.
IIT Bombay, your time is over. The floor is now open to questions from the judges. Seeing as we have no questions, we request a person from the question making team to come up and present the solution on the stage.
For, yeah, so A and B, both of them follow the ARSN mechanism. And Bog deprotection actually forms, so Bog deprotection forms NH, not NCOOH. That is why you have another NH to attack the Cl center that is formed over B. So this is B. You have this Cl center which can be attacked by this deprotected Bog group. This N can attack over here. Same thing over this, same thing over this. So basically the product that we'll have, I'm just drawing a part of it. Same thing and same thing. This is what C is. Now in when you have excess OH minus in the spherical particles, it will, yeah, you are kind of correct that Fe3 plus will be surrounded by OH minus. But since there is excess base, OH minus will preferably abstract this proton and will form COO minus in all the 6 centers. There are 6 COO minus in the entire triazine molecule. One of those COO minus actually coordinates to the PD2 plus center. And so you have a diagram somewhat like this. Suppose O minus and the entire thing. So it kind of completes the octahedral coordination that it has. If we, however, the very next Fe3 plus may or may not have this entire triazine dendrimer moiety because due to steric repulsion. For the catalytic cycle, I'll draw just the main part. So till step 3, it is the exact same thing, except PDCl will be replaced by the PDDMF bond. Now here, the thing is that since a fused ring is formed, the only way that it can form is to do an intramolecular reaction like this. So you have double bond. This hydrogen will come back, aromatize the ring, and you have the reductive elimination over here. So the final product that you'll get is this. When NH2 is present over here as well, it will do the same thing, but not to this side, because if it does the same thing to this side, you have PH-PH steric repulsion. So it will do the, so exclusively this product is formed when if you have a para substituted NH2 group. Now when NO2 is applied, there is minus R effect, so there is not enough electron density present on the NH2 group, so the entire reaction doesn't happen. That is it. Oh, nice try.
With that, we conclude the deep thought round for chemistry Mimamsa.
Thank you to everyone for attending.
I would like to once again extend our gratitude to Professor Srinivas Hota and Dr. Anibar Hazra for judging this. A few quick announcements. We have snacks outside. So the participants, all of you and your team coordinators can proceed for snacks behind the NLH. Also, sir, we would also like to extend you an invitation for the snacks, like after your discussion with the QM team. So guys, I think the team coordinators can start proceeding with the teams, and we can go behind the NLH. We'll be starting the brief thought by 5:15.
All the things.